Okay, first of all, thank you very much for the introduction. So let me first say a few words about Mladen. So I forgot when I met Mladen the first time, but so the first time we shared a longer period of time in the same location was in 2007 at the MSI program. So there were two joint programs. One was in Teichmüller theory, so I was in the one in Teichmüller theory, and Mladen was in the one in geometric group theory. So I had an office facing the bay, that was very nice. And then behind my office was a blackboard, and there were three easy chairs where you could sort of sit and discuss at the blackboard. And then so after a few weeks, we settled in, and then I come in the morning and I see there were three guys sitting in front of the blackboard. It was Mladen, Ken, and Koji. They're probably all here. And they were staring at the blackboard. And so, okay, fine, I didn't interrupt them. Then the next day, I come to my office. Okay, there were three guys sitting and staring at the blackboard. And this went on for a while. I never disturbed them. And then it came to the point where one day I sort of walked to my office, and then actually Mladen was downstairs, so he was not staring at the blackboard. And then I wanted to ask him a question and ask him, Mladen, can I ask you a question? And I said, no, I'm busy working with Ken and Koji. So what does it show about Mladen? First of all, if he starts a project, he finishes it. That's what presumably came out of this staring at the blackboard was the Publication IHS paper that was published in, I forgot when, 2013 or something like this. Then he finds always the best route. So even if he stares at a long time, then at the end he finds exactly the right structure, writes down some axioms, and then the axioms will basically do the job, kill the problem completely. So he never gives up. He always finds the best solution. So thank you for all the inspiration and all the insight that you provided to all of us. Okay, so after this event, I tried to work a little bit on things that Mladen could have also worked on, trying different methods. Of course, this wasn't very successful. So now today, what I'm going to do is I'm trying to tell you something about a project which probably has nothing to do with, or very little to do with what Mladen could have solved, but it uses exactly Mladen's method. So the proofs are a little bit technical, so I will not really go into details of the proofs, but you will get a flavor of what I mean by Mladen's method applied to maybe something else. However, I will start with an old paper of Mladen. So Mladen wrote a paper in 1991, was published in 1991, and it had, let me just copy the right title. It's a very beautiful paper, and the paper is about non-positively curved aspects. Sorry? Oh boy, this starts already badly. I'm sorry. Non-positively curved aspect of finite type Artin groups. So it was published in Geometry and Topology, finite type Artin groups. So it's a very beautiful paper, and it is concerned with finite type Artin groups. Let me just explain to you what those are in case you haven't seen them. So you write down diagrams. So what do I mean by these diagrams? These diagrams define your group. So let me write this down here. Let me take this up and get this down. So diagram means, so the generators of the group are the vertices of the graph. And what are the relations? So here, for example, in the case that I draw up there, so n is supposed to be a line with n vertices. So in the case, the picture I have drawn up has 6 vertices. So they have 6 generators. And what are the relations? Relations are V1, V2 equals V2, V1 if V1, V2 are not connected by an edge. So for example, in this diagram A1, so this is of course not the first one and the second one because they are connected by an edge, but the first one and every all the other ones, which is different from the second, they commute. And so the other relations are V1, V2, V1 equals V2, V1, V2. This is a braid relation. If connected by an edge without label, and so you see that so there are no other relations in the diagram that I drew for the A1 and D1 and E6, E7, E8. And then there are labels for the Bn and F4 and H2 to H4. And there's one other example which I didn't write down because it will also be completely irrelevant for my talk. So in my talk, I will only look at Artin groups that do not have any labels. So, and what is a specific property of these Artin groups that I wrote down on the blackboard? So in this case, the finite type means the Coxeter group. So the Coxeter group is obtained by add the relation bi to the power square is equal to 1 is finite. So in Mladen's paper in '99, he produced a normal form for elements in these finite type Artin groups, and he used this to show that essentially these groups from their geometry, I mean geometry meaning of course the geometry of a Cayley graph, behave very much like groups or say spaces which are non-positively curved. Of course they're not negatively curved because you have all these sort of commuting subgroups. So for example in this AN case you see very clearly that there are embedded subgroups that are isomorphic to z to the power k, where k is less than n over 2. And so on and so forth. So these are very clearly very different from hyperbolic groups, but they behave basically like groups of non-positive curvature. Okay, so now I will not be interested in, as I say, in specifically these finite type Artin groups. Let me define what a small type Artin group is. A is a small type Artin group. If defined by a diagram, by such a diagram in the same way. So my diagrams are all connected. I will not repeat this. This is going to be a standing assumption by diagram without labels. That means we have only commuting relations. And braid relations. Now, this seems to be, in a certain sense, simpler than these groups Bn or F4. But the problem is much less is known. So the Coxeter groups, if you don't have one of these AN, DN, or E6 to E8, the Coxeter groups are not finite, and then things become much more complicated. For example, some foundational things are not known for these general small type Artin groups. In the case of the finite type Artin groups, we can write down explicitly a classifying space, which is sort of related to the idea that these finite Coxeter groups are Coxeter groups that act as reflections on some Euclidean space, Rn, where n is a number of vertices, so it's a discrete group of reflections. And then what you can do is you can complexify, and then you do the following. You see that a reflection, if you have this relation here, vi square is equal to 1, that is a reflection, so it flips over along a hyperplane. But then instead of flipping over, you go around the corresponding complex hyperplane, which is now complex codimension 1. You go around it once, and this describes a circle somehow, and this is corresponds to the generator of the Artin group. But the problem is for these small type Artin groups, we don't really know what the classifying space is. There's foundational work of Charney and Davis, but that don't cover all the cases. So there's many open questions. What I will be interested in is the relation to the mapping class group. So what I will be looking at is denoted by mod S. Let me be more specific. Mod S GM, the mapping class group of a surface of genus G, and I will only be looking at a surface of genus at least 2 later on, a little later on also at genus at least 3. Let me write it on genus at least 2, and M, because then 0 punctures. And now we know already that there is a nice relation to these small type Artin groups. Namely, we know that mod S 0 and also 1 can be generated by Dintwiss of a Humphreys generating system. So what is this? Let me draw a picture here, maybe genus 3. What we just do is we draw our favorite surface, then we draw the following simple closed curves on the surface. Now you see this system of curves has the following property. So if you cut the surface open along the curves, you get, in this case, 2 disks, topologically. And now you look at the Dane-twist about these curves. So TC is supposed to be the left Dane-twist about a simple closed curve. Let me denote the simple closed curve by SCC, simple closed curve C. Then we have the braid relation. So that means so what do you know about the braid relation? Let me write this down because it's going to be not unimportant in the sequel. So we know that if CD are disjoint, then the Dane-twist commute. That's pretty easy. TD is equal to TD dC if CD intersect in a single point in one point. That means if you can isotope these curves so that they have just exactly one intersection, then if you look at the left Dane-twist, you get the braid relation TC/DD. TC equals TC/DD, TC/DD, the braid relation. And then next, if CD intersect in bigger or equal than 2 points, then it's known that these Dane-twists generate F2, the free group in 2 generators. So there's then no relation in this group. So it's a pretty simple somehow set of relations that these Dane-twists fulfill. So Humphrey showed that the Dane-twist along this particular curve system does generate the mapping class group. And now let me recall a paper by Matsumoto. So Matsumoto, this was published, let me just check this out here, in 2000. So Matsumoto says that the mapping class group tries very hard to be a finite type, a small type Artin group. So what does it mean it tries very hard? So we have here a curved diagram. So what I mean by curved diagram, this means that vertices the simple closed curves from the curves, the simple closed curves from the system, simple closed curves, intersection, so edges equals to intersection. So here, I'm very careful here. So in the sequel, when I talk about curved diagram, I require always that there's a most fine intersection between two curves. So you see a curved diagram. In this case, it's a curved diagram that is given by this picture here. Let me see that this is correct. 1, 2, 3. So this defines a diagram which is of small type. This defines an Artin group which is of small type, but this is not of finite type here. And so what Matsumoto showed that the only additional relation, so here you have the braid relation, this defines an Artin group, and the only additional relation are as follows. So what you do is you look at this. Maybe I want to take some colored chalk. So we know that in the finite type Artin group, so this defines a finite type Artin group. This is the Artin group A4, because you just have one segment of length 4. And so these finite type Artin groups have a center. So that C of gamma be the center, the generator of the center. This is a so-called Coxeter element. So the center is infinite cyclic of the finite type Artin group. Let me abbreviate this like this. And so if we take the center of this group and we take the center of this bigger group, this is A5, then in the mapping class group, we have the following relation. So this is, was figured out by Matsumoto. We have C of A5 is equal C of A4 square. And we have one more relation which goes as follows. So we have here the diagram, let me see. So we have the diagram E6. Sorry?
2 times it? Or I see.
Yes.
Okay, 2 times it.
Yeah, so you look at the blue guy, right? So then it defines, an element, right? So you look at the corresponding Artin group, you take the corresponding generator of the center, and then in the mapping class group, this exactly, it's queer. It's exactly the corresponding element that is defines the center in A5. And then we have one more relation. So we have here, so now I have to maybe redraw the picture so that you can see it. We can look at, so hopefully I corrected. So this is E6, the diagram of E6. And this is, we have a diagram of E7. So, and then we want that C of E6 is equal to C of E7. This is also finite type. Let me write down this here. E7. And then we have one last relation in the mapping class group, which means that if we take, again, this is a picture. I hope I get the number of the dots correct so that you get actually exactly the Humphrey system is probably not correct, maybe something like this. Then you know that you take this Artin group and then C of A 2G minus 2G is equal to 1. So that goes, that disappears. And what Matsumoto showed is that this is the only relation in the mapping class group. So the mapping class group has a presentation that is entirely defined in terms of Artin groups. So let me maybe.
Numerical groups are completely independent.
Yes. Yeah, but I'm saying that all I'm saying is.
I get it.
Yeah. So there is a relation between. There's a relation between. A strong relation between Artin groups and mapping class groups. Okay, so now let's try to remember another two results. So there's a result of Weinrib. I have to copy his spelling, I can never remember. He showed that any homomorphism of E6, now E6 stands for the finite Artin group into E6, which maps the generators to Dintris into some mapping class group, any mapping class group, which makes the generators to Dintris has a kernel. An infinite kernel. No, which so kernel infinite might just mean that I kill the center, which descends to. It's not quite the way you described it, but. Which descends to the quotient. So in other words, if you try to map it, and you not only kill the center, but you also kill quite a bit of the rest of the group. So it's more mysterious than it looks like. And then, however, there's a theorem of Perron and Vanier, which says that the Dn group, the finite type Artin group Dn, so the An group, so let me recall that the An is a braid group, the Artin braid group in n+1 strands. So this is a mapping class group of a sphere with one boundary component and a number of punctures, and the Dn embeds into mapping class group into mod S2n. Maybe I divide it down. Dn plus 1 intersects into mod S2n with one puncture. That's what's known to date. So let me furthermore point out that now we are will be more interested in the mapping class group and the more precise relation to Artin groups. Let me point out that fact mod S, say mod S G0, cannot be generated by Dintris about 2G curves. That's relatively easy to understand. So this means that the Humphreys generating system is the smallest system that you can have. So why is that true? Let us assume, we do something stronger. We require, question what happens if we have 4 curves with curve diagram. So curve diagram meaning exactly what I wrote down before. A tree. So the Humphrey system is a curve diagram with a curve system with curve diagram, a tree. That's the way it is defined. But let's just take now any curve diagram and any diagram that is a tree. So let's assume we can generate the, so we know, assume we can generate mod S G0 by such a diagram that consists of 2G curves, and then we have the Dintris about that curves. So we know that mod S surjects, let me write it down mod S instead of mod S G0 for brevity, surjects onto SP 2G Z mod 2Z. Okay, So the mapping class group acts on homology of the surface. The homology of the surface with Z mod 2Z coefficient is just the free vector space in, so it's basically Z2Z to the power 2G. So it's a vector space of dimension 2G over Z mod 2Z. And now we know that this mapping class group surjects onto this, but we have an invariant. Now I have to find out what the best way to maneuver this blackboard is. So we have an invariant here, which goes as follows. So invariant. We take now the element, so we have a curve diagram. So maybe it looks like this, graph like this. And so we take the vertices equal to the generators with, say, 2G vertices. And we take the vertices to be the generators of Z to the over 2Z to the power 2G. So that's now a vector space of dimension 2G. So we think now as a sort of a vector space which is spanned by these vertices. And now we can define a quadratic form on this vector space as follows. So write down an element. Let me maybe abbreviate this by H of H. It's of course a unique basis representative. Can be written as, and now we take just the sum, right? AI, VI. So VI stands for the vertices here. So this is a basis. And now I look for the AI is equal to 0 or 1, because we work with Z mod 2Z coefficient. And now I just define Q of this sum here is equal to the Euler characteristic mod 2 of the complete graph spanned by the vertices by VI with AI equal to 1. So for example, if you have just a generating set, this would be, we get 1 point here, and then the Euler characteristic mod 2 is 1. If we have two things connected by an edge, right, so this is here, you can see what the Euler characteristic is also 1. But I mean, if you have two so if it looks like this, so you have here, this is you have here an A, you have here 1 and here 1, and so here's no 1 in between, then the complete graph would consist of two vertices, and then you would have the number 0. And so this defines a quadratic form. I will not define precisely for time's sake what this quadratic form is, why is this supposed to be a quadratic form. And now you see that this quadratic form has an ARF invariant. So Q has ARF invariant. So Q has ARF invariant. So this can be 0 or 1. It's a number in Z mod 2Z, can be 0 or 1. And the Rencontres about the curves preserve this invariant. And now you think about the following. So these curves, if let's assume we had such a generating system, these curves have to span the homology because the homology has to sit somewhere. So then you know that this ARF invariant is an invariant of the subgroup of the mapping class group that is generated by this system of Rencontres. And here you see that you cannot generate the mapping class group with 2G elements. Okay, so what can we say now about the situation here? Here's something that, let me write down a theorem. That's the first theorem for this talk, which I have to say is a little bit of a surprise to me. Following theorem which comes out of a very recent work of Calderon and Calderon and Salter. And this, so part of it is due to Calderon and Salter, and part of it is due to myself. So I combined it in one theorem. This is bad taste, but I tell you later who did what. So here's this fact. So let C be any curve system on S such that the curve diagram is a tree. S minus C is a disk, one disk. And and the number of curves is 2G. So we are exactly in the situation that is sort of we already figured out that these the interest along these curves will never be able to generate the mapping class group. Then the group generated by the interest about C, curves in C, is of finite index in mod S unless the curve diagram is a line to be under great group case. And furthermore, what kind of groups do we get up to conjugation? So let's assume we are not in the case that the curve diagram is a line. Up to conjugation, there are only two groups. So what does it mean is, it means that regardless what kind of diagram you write down, if you're not in the case where your diagram is a line, then you generate a subgroup of finite index, and up to conjugation, you will never be able to distinguish groups up to conjugation, so only up to conjugation. So up to conjugation, you only get two groups. So why is that true? So the rest of my talk, I will partially explain why this is true and what it has to do with Artin groups. So I will not, of course, needless to say, I will not be able to give you a complete proof of this. So what Calderon and Salter showed is, so let me point out what their contribution is. They showed that there's one curve diagram. So basically, what they figured is that there's one curve diagram of this, which consists of 2G curves that generates a specific finite index subgroup of the mapping class group. And what I showed is that basically there are only three types of groups that you can get. I mean, the group with a line segment is very special, because if you think about it, if you have a line segment, then the curves are all aligned on a line, and there's a hyperelliptic involution which centralizes group. So this group is essentially an embedded braid group in the mapping class group. So you will never be generating a finite index subgroup of the mapping class group unless you are in genus 2. So this is a result about, and I forgot to have here an assumption. So G is supposed to be for the result of Calderon and Salter. G is supposed to be bigger or equal than 5. For what it is, you don't need anything. So except that you don't know exactly what you get, but you only get finite two types of groups. That's always true for any G. But if you want to get these two types of groups that are finite index and specifically described, you need the result of Calderon and Salter. Okay, so let me show you a little bit what it has to do with Artin groups. And oops. I was not supposed to do this. I guess I was supposed to. I'm very sorry for this. So I was supposed to get this down. Now get this. This was long. No, this was not good. Okay, so. Okay, I didn't press hard enough. Sorry for this. Okay, so. Okay, so let me try to explain to you what it has to do with Artin groups. Oh, this is not the one. I'm not doing a good job here. Sorry, failed my exam. So where does this come from? So we try to produce a normal. So let me go back to Artin groups. We try to produce a normal form for Artin groups. There's no, I don't know anything. So for finite type Artin groups, Besvina wrote down this normal form, which required that you have the Coxeter element, which is very nice, and then there's some positivity assumption and so on and so forth. But what we will do instead of, we'll do sort of try to find a normal form, which is a little bit, a normal form is a little bit too much said, which tries to not be of the type that Mladen wrote down, but tries to be.
That was the mean, not me.
Sorry?
Normal form for.
Yeah, but you did the sort of all the geometry. Yes.
Yeah, okay. The normal form is the mean.
Yeah, normal form is. Oh, there's also a paper by Briesbrunn and Saito. Yeah, so they produce normal forms. There's more general. But for the geometry is rather useless. I mean, I stared at this, I don't know, forever, and it couldn't make anything out of it concerning the geometry. So we will rather try to do the following. Here's this one simple fact, right? If we have ABA is equal to BAB, well, this is our enemy, right? I mean, so this is a relation we don't understand. Then we could sort of have a preference for A over B, right? If we prefer A to B, then we would replace any expression like this by this one, because it has more A's, right? And we would try to reduce the B's. So what does it mean is we will distinguish our generator. So assume now we have a tree, have a curve diagram or an Artin diagram, or it's in some sense I would think of it as being the same thing. We have a tree. And then a tree is a bipartite graph. And what does it mean is I can color the vertices. So alternatively in say black and white. So have black and white vertices. And I color one of these vertices white, and I say this is my preferred color. So I color one white. So I pick any vertex, I color it white, and then this coloring determines the rest of the coloring, because I have a tree. And this means that, I mean, whenever I see a braid relation, so I think about the edges of this diagram defining a braid relation. Whenever I have a braid relation, then I will know what to prefer. So if I have a white, if A is white, then I prefer A, so I will replace this relation by that one if I can, and then I try to reduce the number of black vertices somehow in my expression of the element in the group. So now what you do is, now I do exactly what Mladen told me to do. So I use the idea coming from, yeah, I don't know, probably goes back to Thurston, but I mean, Mladen figured out that if you want to process out Fn and basically generating sets of the free group in N generators, that's actually the way to do. I always was resistant to using it, but now let's do folding, okay? So that's Mladen introduced us to folding and advertised folding, so let's do folding. So how do we fold? So now let's make out, so in the setting of my curves, the coloring, so the coloring determines an orientation. So I tell you what that is supposed to mean. So now I'm thinking about as having this, this diagram realized by curves on my surface. So now I can draw a picture. So I have my white vertex, right? So here's my white, let me assume I have a white vertex. So I now take my an arbitrary orientation for my curve going around, which is represented by this by this vertex in the diagram. And I know that this now determines an orientation for a curve that crosses through. How is this supposed to be? This is white. So now if I look at this curve here, so I want that this curve here is oriented in such a way that, so this is now a black vertex, right? That the orientation of C prime, here's I have for a brevity, I don't write this down explicitly. So you have an intersection point as C prime of the point P, and D prime of the point P is positive. And now I think about sitting on an oriented surface, so this makes perfect sense, right? As soon as I determine the orientation of the yellow guy, I have the orientation of the blue guy. And then if I have the orientation of the blue guy, so I want that this holds for every curve that crosses through this determined orientation, for every curve that intersects the first one. Since I have a tree, I can basically keep on going and get all the orientations of the curves aligned in this way. So once I have an orientation, I can make the following picture. So now I have this picture here, and I replace it by, so now I look at the oriented picture. Let me assume that this goes like this. Then I'll replace it by our favorite picture, which is like this. And I want to remember the orientation. So this means I replace it by this oriented piece of graph. This looks like a train track in whatever sense, a train track in the sense of Thurston, train track in the sense of Mladen, right? So you have here gates and where you have incoming and outcoming. And I want that I can actually continue exactly with the orientation. That means if I come in here, so this arrow means I come in here from this direction, so I'm allowed to move on in two directions, which is given by these arrows. So I get an oriented train track. And now associate to this train track, I call it tau, an Artin group, small type Artin group. A of tau. How does this go? So what I do is, I want one more structure, and this is a ribbon structure. So I assume that I'm thinking about living on a surface, but what's really relevant is a ribbon structure, which gives us, so ribbon structure is nothing else by being an ordering at the vertices here. So meaning that I know what is to the right and what is to the left. So if you fatten this to a surface, so you take so assuming that there's a graph lying on the surface, then it gets a ribbon structure from the surface, right? Because you think of it as having here a small neighborhood, tubular neighborhood, everything is oriented, surface is oriented, and then you know exactly what's to the right and to the left. And this is a ribbon structure, remember, as ordering. At the vertices. So at each vertex I have directions. There are incoming directions and outgoing directions. I arranged in such a way that at every vertex there's both incoming and outcoming, as we are required from a train track. So we have this additional ribbon structure, and then we can define what an intersection means. So we want that the vertices of A of tau are the simple closed curves, embedded simple, or say embedded closed curves. In tau. Okay, this makes sense, right? If you start with the curve diagram here, then it's not hard to check that what you get exactly the original curves back. So these are the generators, the generators of A of tau. So what is the relation if CD can be realized disjointly. So what does that mean is this means that they may intersect in the graph, right? It may look like this. But so if this is C, and then goes out in this way, and this is D, and it goes out in this way, then you can think of it in the ribbon graph. You can actually get rid of this intersection by a small homotopy. So that's what we want. Then we want that. So if there's all the intersections potentially in this abstract graph are given in this form, then we want that CD is equal to DC. So this is viewed as generators of my Artin group. So if C, D intersect in one point, so what does that mean? Of course, we discard all the intersections that look like this. However, if we have one of intersection that looks like this, right? So it could be that C comes in here and goes out here, and D comes in this way and goes out in that way. Then we want that the braid relation, and I don't want the braid relation. Everything is oriented, so I will place here every black vertex by its inverse in the braid group, and I keep the white vertices as they are. So I have a preference for the white vertices. So CD minus 1, C is equal to D minus 1, CD minus 1. It's exactly the braid relation, except that I keep now the orientation, and I have a preference for my white vertices. This is what it says. And if CD intersect in bigger or equal than 2 points, then I want generate F2. No relation. So this means now abstractly to each of these gimmicks, you can associate a nice Artin group. I'm not saying that these Artin groups are all the same, but now we can have a processing in Artin groups. So what is a process in Artin groups? As we are folding. And now I run out of time, so let me just, so Mladen tells us that we should fold, so let's fold. So what does it mean, fold? So let's try to have this picture here. So what we can do is we can fold, everything is oriented, we can fold that edge over this one. This doesn't help much. I'll tell you in a second why. So if we fold this edge over this one, then we basically have the following, a new structure here, new graph, right? So why is this not very helpful? Because now we can do this backward and fold this guy over that one, and we see this exactly the same picture. That's not really helpful. So what we need to do is we need to do fold in this way. If we see this picture here, then we can fold this one up, and we cannot reverse it. And so folding. So let's assume that eta, so if eta folds to tau, in this picture here, nothing changes, the groups are the same, there's natural homomorphism, but in any case, if eta folds to tau, then there exists a homomorphism. So this is what you have to verify. Exists a homomorphism F of A of eta, which in general may be a discrete Artin group, to A of tau. And how does it go? I mean, the only thing, since the relations only sit in the generators here, the only thing that you have to verify that you can write down images of generator, and then you have to verify that the relations are fulfilled in the new group. So that's what it comes to. Now you can exactly see what you are supposed to do. You're supposed to keep track of how you process these Artin groups by doing the folding construction. And now what you want to do is, so here you have your particularly nice Artin groups that come from these curve diagrams here. What you want to do is, you want to say that if we sort of have such a diagram, there are only finely many possible diagrams, simply because here everything is finite, right? And so the folding operation remains in a finite sort of set of configurations. So if you go from one of these particular nice diagrams to one that is sort of sitting down, that you actually get an isomorphism of groups. And this, so then it might factor so something that is much smaller and might have kernel and might not be surjective. But the point is here, what you have to show is that you get an isomorphism of groups. And then you pick up, on your way of having these isomorphisms, you pick up other groups that are defined by other curve diagrams. And what you realize is the only obstruction to both of these curve diagrams is, I mean, assuming that, say, if you go back to the mapping class group, assuming that we were not in the case of the Artin break group, is the only obstruction is the alpha invariant. And that comes from the moduli space of abelian differentials, which I cannot explain to you now. Thank you for your attention.